All right, so today we're going to talk about logistic growth and Newton's Coulomb law. So there were four types of differential equations for which were responsible in BC calculus. The first two were covered in AB. So these are the first two you probably should remember. And now we have another two types. So that type 3 is this one right here, which is logistic growth. All right, so what logistic growth, what it's for is, so if you ever have a problem that, for example, is talking about population, you're going to have a limiting factor, right? A limiting factor means that, for example, if you have something like population growth and that happens to be exponential, well, that cannot grow without bounds. There's a certain point where that is going to basically level off. Okay, and then we're going to see what we're talking about here in a second. So let's take a look at it, right? So this is one that it's important. That's the third type of differential equation. All right, and notice that right here, L happens to be the limiting factor, P is population, K is a constant. All right, so K and L happen to be positive constants, okay? So now, how fast the population is growing depends on this differential equation, all right? So now we're going to do separation of variables to solve for this. So first, let me see. I want to screw this up too far. Okay. So again, we're going to multiply the right side times dt, and all we're going to leave on the right side is the k. All right, so again, I'm going to use separation of variables. So this is going to be dp, and everything that has a p over here, mainly all of this, I'm going to divide both sides by that. So I have p 1 minus p over L is equal to the integral of k dt. All right. So now, as we go on, all right, there's this little piece of information that would definitely help you out with this. Right. And by the way, and the steps are here on the right side. All right. So we're going to try to integrate both sides. But before we do that, all right, we got to find a way to basically separate some of the stuff. So what we're going to do first is we're going to say that 1 over p 1 minus p over L, right? If I find a common denominator, so I'm going to write an extra step here. If I find a common denominator in here, that would leave me with p L minus p over L. And because of the rules that keep, change, flip, right, this L is right here. When I keep, change, flip, that's going to flip that L, and that L is going to end up on top. So I have p L minus p like that. Okay, and then now we're going to use some separation of variables, which I'm not going to do on this because we're going to do another example like this, so you'll see me do it. But when I use separation of variables, not separation of variables, but partial fractions, now would end up with something like this. Okay, so now all of this right here is now going to become two integrals. One integral that goes between 1p dp, right? So that's going to be a lot easier to integrate, plus the integral of 1 over L minus p dp. And remember that L is a constant, okay? And that's going to be equal to the integral of kt. And again, k is also a constant. All right, so when I integrate this, okay, I'm going to end up with the natural log of the absolute value of p minus the natural log of the absolute value of L minus p. Remember that it's a minus natural log because when I try to use substitution like this, for example, right, where L is a constant, du would be negative dp. All right, so if I use substitution, that's what would happen. So that's why I have a negative there. All right, I hope you understand that, but if you don't, let me know when you see me. All right, now this side, and I kind of wrote this wrong. This is dt over here. This is going to give me kt plus c. All right, and now we're going to try to simplify this. So we're going to do something that may seem a little weird. We're actually going to multiply the right side and the left side by a negative. It will make this a little nicer. So let's just go ahead and do that. And at the time, I didn't really know what that's going to make it nicer, but it kind of does. Okay. So I'm going to use the properties of logarithms to bring this stuff together. So I have natural log of the absolute value of L minus P over P is equal to negative KT plus C. Excuse me, minus C. It really doesn't matter, really. You can call it plus C because kind of like when we did separation of variables earlier in the year, this is going to become some kind of constant. So we'll see here in a second. All right, so we're going to now do the exponential of both sides here. Right, and that's going to leave me with L minus P over P is equal to E to the negative KT minus C. And again, you can write that as a plus C. At this point, it doesn't matter because just like stuff we talked about before, right? Remember that this right here would be the same thing as having something like this. And this right here is just another constant. All right, so we're going to rewrite this as L minus P over P. And now they chose to express that constant as the letter capital A, which is fine. Okay. And then at the end, they do, essentially, I want to solve for P here, right? So the whole goal is to try to get an equation that has P. So what I'm going to do here first is I'm going to multiply both sides by P. I mean, this could be, you may already see where this is going. You may not. If you do, awesome. But if you don't, just hang in there and I'll show you how we're going to get P by itself. All right. Now we're going to add this P on the left side to the right side. And then we're going to factor out a P. So this is L is equal to P1 plus A times e to the negative KT. All right, so then finally, if I divide both sides by this stuff right here, then you're going to see that I'm going to end up with P is equal to L over 1 plus A to the E to the negative KT. Now, I guess you could try to memorize this formula. I mean, I'd rather you didn't. There's already enough stuff to memorize in this class, but we can definitely derive that later. All right, so again, we just solve for, in this case, P, which is part of population. So let's go ahead and move on, all right? So what we call the carrying capacity, all right? What this means is this is the max population the environment is capable of sustaining. So again, this differential equation is really a more realistic type of function, right? When it comes to population specifically, and other uses that we're going to talk about later. But think about it, right? As the population goes to 0, then dP becomes Kp. Oh, excuse me. All right. dP becomes Kp. and as P approaches, so as this population approaches this line right here, hopefully you can see over here, as you approach here, right, then dP becomes 0. So as you approach the the carrying capacity, all right, the limiting factor, then the derivative is going to go to 0. Okay, so now let's talk about what number 3 is asking. Right, it says the graph of the function P is called a logistic curve, and logistic growth, the population grows the fastest when the population is half the carrying capacity. All right, so again, what that means is that the max value that means that that's when the population is at half of the carrying capacity. All right. So to find, so again, these are all facts of differential equations like this. To find the time of the max rate of change, and that's going to be 1 over k times the natural log of a. Okay, and again, we're going to do some problems that kind of illustrate what's going on, right? So it says the slope are the smallest, right, when you're near, and I guess I'll start writing some stuff on here. So this line right here, all right, that's the carrying capacity. So we want to put it all together here. This right here is the max slope, which is located at a point of inflection here. My point of inflection would just switch from concave up to concave down, or vice versa. All right, and this right here, and I'm talking about that curve basically from the beginning to about right there to where it hits the max slope. That's an approximately an exponential there. All right, so it's an approximate exponential. So that curve is approximately exponential right there. Okay. Okay, so back to this now. So the slopes are smaller. Note that the slopes are really small here, right? And they're really small up here. So at P is equal to 0 and P is equal to L, or when the population nears the carrying capacity. Now, they're going to be the steepest around the point of inflection, which in this case happens to be half of the carrying capacity, right? And now, if for some reason this population goes above this carrying capacity, right, above that, so there's not really a horizontal asymptote, but if you get above that somehow, all right, then what's going to happen is that the slopes are going to become negative, and the population is going to start declining because they cannot sustain such a population, right? So you can kind of think about as resources, right? You cannot have a population that just grows infinitely forever. It's impossible. All right, so now we're going to be reading features from the slope field. All right, so an example to a population of coyotes in the wildlife preserve is modeled by a logistic function. The preserve can support no more than 100. All right, so that's kind of important. All right, on the property at any time. So we're going to write the differential equation out. The differential equation is the one that we just dealt with, right? The logistic one. That the change in population over time approximates this differential equation, where k is a constant, p is the population, right? And L is the carrying, what do we call it? The carrying capacity, meaning that's basically a limiting factor, right? Which happens to be right here. So that's going to be L for me. At this point, I'm just going to plug it all in. All right, so I have 0.1 for K, which is right there. P1 minus P over 100. And so remember that this is dP dt. This is how fast the population is growing in this case. All right, I'm going to do a little bit more of, I don't really know why I'm doing this, but according to the notes that I have, if I want to have a more simple equation, I could write this like this. If I find a common denominator here, right? Now remember that this 100 here, I can divide that by, that's the same thing, right? I can write that 100 here or here. It's actually the same thing. So what I do from here is that when I divide both of those by 100, I move the decimal point over to the left twice. And I end up with this. Now, honestly, though, if you're gonna use a calculator and they want to know how fast the population is changing, all right, then I would just probably use any of those formulas. They work just fine. All right, it says the slope field is shown at the right. Where does the horizontal asymptote appear to occur? So you can kind of see, right, that it gets really, really flat right here. So that's about 100, which makes sense because that's the carrying capacity. Okay, so what happens if the initial population is above the asymptote? Well, again, like we said before, if it happens to be above the asymptote, you can kind of see the slope fields, right? And the population actually begins to decline. Again, let me erase this line because I don't need it, but that's the idea behind it. Whoops. Will decline. It would be overpopulated for that preserve, right? So on D, it says the preserve initially begins with 20 coyotes. Sketch the graph of P of T in the slope field. So if I'm just sketching a graph here, right, I can just try to follow these lines as best as I can. And it would be something like that, right? So that's what it would be like. All right. Okay. That's the sketch. So let's go on to E. All right. So E is basically where I'm going to almost do exactly what I did at the beginning of the notes, but this time I actually do have numbers, all right, to go by. So remember the dP dt. (0.1p minus 1 minus p over 100). All right, so don't forget that this came from the formula that we had at the beginning of the notes, which I'm going to write up here, where we had kp1 minus p over L, right? Where L is the carrying capacity and K is a constant. Okay, so now what we're going to have here, right, we're going to have to integrate. So we're going to do exactly the same steps as we did before. So we're going to use separation of variables. So let's see. So we have dP over. So, don't write too large here. It's definitely going to take some work. This is going to be over P1 1 minus p over 100 is equal to the integral of 0.1 dt on this side. All right, so now doing exactly the same thing that I did earlier, which I guess I'll write over here, which remember that if I wrote it like this, if I found a common denominator, all right, so if I found a common denominator, I would have that. And then this, I guess I should probably write it. This then would become, if I keep change flip, 100 over p, 100 minus p, dp is equal to this. Okay, so now I'm going to actually use the partial fractions, but this time I will show you how I'm going to get what I'm going to get. So I'm going to grab this. So the whole goal is to try to make this into some kind of integral that I can actually integrate, right, with the skills that I now have. And again, I'm using partial fractions here. All right, so here we go. So if I multiply both sides by the common, or by p times 100 minus p, I would end up with 100 is equal to a times 100 minus p plus bp. Right now, if p is equal to 100, well, then all I'll be left with is bp, or excuse me, 100 is equal to 100b. So b is 1. And if I do the same thing, but now I'm going to say that p is 0. So if p is 0, then that would leave me with 100 is equal to 100a, which means this a is equal to 1. All right, so now I'm going to write what I have over here so you can see what I'm doing. So now I can actually separate that integral into 1 over p dp plus 1 over 100 minus p dp is equal to the integral of 0.1 dt. All right, so this is going to be the natural log of the absolute value of p, minus the natural log of 100 minus p. That's equal to 0.01 t plus c. All right, now we're going to multiply. We're going to multiply by -1 to make it nicer. So that's going to give me, I'm going to write this one first. Okay, so I'm going to write that as a positive natural log of 100 minus p minus natural log of the absolute value of p is equal to 0.1 t plus c. I'm going to use my properties of logarithms to put that together. So I have 100 minus p over p. And this is going to remain the same. Now I'm going to use the exponential on both sides. And then basically, dang it, I forgot to do something here. I forgot to switch that to a negative. And that's, see, if it's negative, who cares? It's going to end up being the same thing. So, but I have to make this negative, I'm sorry. So now this is going to then become 100 minus p over p. And for the same reasons I talked about earlier, that e to the c, right, if I separate this, I'm going to end up with another constant, which we're going to call a in this case. All right, so remember that what we're doing is finding the general solution, right? So we actually want to find out what a is going to be. And at this point, I can, if I want to, go ahead and plug in the 0 and the 20, right? So we're going to plug in the initial population of 20. So now we have, let's see, 100 minus 20 divided by 20 is going to be equal to a e to the 0 power. So long story short, a is equal to 4. All right. Now I'm going to continue on and try to basically get p by itself pretty much the same way that I did it earlier. All right. So now I have, I'm going to come over here to this side over here. And I have 100 minus p over p is equal to 4e, all of that. All right. So again, my goal is to try to get p by itself. All right. So don't lose track of what I'm doing. I'm going to multiply both sides by p, which is going to give me this. I'm going to add the p on the left side to the right side. And then I'm going to factor out a p. So that's basically the key step to make this go from having 2 p's into having 1 p. And then finally, I'm going to divide both sides times 1 plus 4e to the negative 0.1 t. So p is going to be equal to 100, yes, excuse me. 100 over 1 plus 4e to the negative 0.1 t. Whew, that was a lot of work. All right, but that's the answer for that. Let's see. Let's move on. I'm gonna do something here. Then you're gonna see why. So every now and then you have questions like F and G, where it's asking you when, which is talking about time. Okay, so in this case, I'm going to use this function that I just found, and I'm going to solve for t. Okay, so I'm going to do it off to the side because I want to be able to have one formula that would give me time, so I don't have to rework the formula every single time, right? Because that can be pretty tedious. So I'm going to do it once, and I'm going to be able to use that formula. Okay, so here we go. What we're going to do here is we're going to solve for t. So first, we're kind of going to go backwards. Let me see where I can start. We can really, let me see where I should begin. Actually, I'm going to start right here, all right? Because I'm trying to get to basically t, right? So every step you're going to see me do is just going to be backwards. So I'm going to start from right there. I'm going to solve for t. So again, I have 100 minus p over p is equal to, in this case, 4e to the negative 0.1 t, all right? So now I'm going to divide both sides by 4. And this is going to look really funky, but oh man, I'll always do that. I have 100 minus p over p, all of that divided by 4. Maybe how did I get this equation? How did I do this, fellas? I don't know. Oh, okay. It's fine. Okay. Let me start over here. I'm sorry. There was a simpler equation that I used, but I cannot quite remember where or how I did it. Oh, I see. It'll be fine. I'll stick with this one for now. So if I divide this by 4, whoops, I'm on the eraser. If I divide this by 4, essentially what I'm going to have is e to the negative 0.1 t is equal to, this will be the same thing as having this, I believe. I sure hope so, because I'm flying blind right now, fellas. Who knows? This could be completely wrong. We'll find out. I'm going to use the natural log on both sides now. And then now I'm going to divide both sides by negative 0.1, which I can really write as 1 over negative 1 over 0.1. That is a very interesting number. I guess if I didn't have a calculator, I would tell you that's just 10, or negative 10 in this case, times the natural log of 100 minus p over 4p. So I guess I could write it like that. And at this point, the pressure's on me. Hope this works. All right, so I know that seems like a lot of work, and it sure is, but I'm hoping that I can use this equation for this question and the next one. All right, so let's see, negative 10, natural log, and then now instead of p, I'm just going to plug in an 80. All right, so I have 100 minus 80 over 4 times 80. Okay. Luckily for all of us, it worked. All right, so again, what I did here is I plugged in. All right, so plug in 80 for p, or p is equal to 80. And when you do that, you get approximately 27.726 years. That's a That's how long it would take for the population to go up to 80. Now it says, when is the population growing the fastest? Remember from what we wrote earlier is that it's always growing the fastest where is the carrying capacity divided by 2. In this case, the carrying capacity is 100 over 2, so this is 50. So that's going to be the population when it's growing the fastest, right? But it's asking when. So I'm going to use exactly the same formula I used over here that I came up with, all right? So, but instead of writing uh, P, I'm going to write a 50 over 4 times 50, like that. I'm sure you can simplify that further than what I did, but I don't feel like it. If you want to do it, you do it. So this is 13.863 years. All right, so that's that. All right, now it says find the limit as t goes to infinity of p of t. So basically, you can even look at on this, and it would be the same thing, right? So you can actually look at the graph and come up with the same answer. But if you were to take this equation, remember this is p of t, that one right there. If I put an infinity or a really, really large number for t, that is this would actually go, and let me just go ahead and write it. So we're on the same page here. If I were to write a really, really big number for t, this number would go to 0. So I would have 100 over 1, which is 100. Okay? But you can also tell from the graph. Remember, they talked about this being like a horizontal asymptote. And also, if I started on 20, you're not really going to go above the carrying capacity. All right? So our final differential equation that we encounter in BC involves Newton's law of cooling. So this law states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and some fixed constant. So just like we talked about in the past, right? If you have some kind of liquid, whether it's like really hot liquid, is not going to cool it's not going to cool beyond the temperature of the room, for example. All right. This is also very useful for falling objects approaching terminal velocity, right? In the real world, if you drop something from a really high place, terminal velocity is basically going to make the velocity be terminal. It's not going to go any faster. But we'll just do this problem that we have here in front of us. All right. So hang in there. And I've been going pretty long, but just the way it is. Okay. So now we're going to go to example number 3. And if you read the problem that talks about that you bought this frozen coffee treat, all right, and your car is always kept at 65 degrees. Traffic was terrible and you spent 10 minutes getting to the high school. This is the drink warm to 35 degrees Fahrenheit because you checked it with your temperature probe at the red light. I know we all carry those. I mean, I sure do. Then 2 students had a rear end collision. Another 10 minutes passed. All right. So by that time, 20 minutes have passed since you bought that. You check your drink again and it has warmed to 50 degrees. This is use Newton's law of cooling to estimate the following. All right. So here's Newton's law of cooling. Okay. Where Y really stands for the difference in temperature over time, right? So dy dt is the difference in temperature over time. So let's go ahead and write this. All right, so step number 1, we want to write this equation, right? And notice that what I'm looking for is what was the frozen coffee's original temperature. So what I want to do, right, before we start doing it, is I want to find the solution to this differential equation. Okay, and I want to figure out, and I'm going to use that equation, and I'm going to plug in 0 for t, which is for time, and I'm going to figure out what the original temperature of the drink was, or this frozen treat, whatever this was. K is a constant. Remember, Y stands for temperature. In this case, B is going to stand for the original temperature. or I'm sorry, the temperature that it was at a certain time. I guess this is the solution where we're going to get. All right, so if I do everything correctly, we should have a solution that looks kind of the same. Okay, so let's do that. I'm going to show you how this works. So now, this one happens to be a lot easier. I will use separation of variables again. But this one is a lot simpler to solve than the logistic curve that we were doing earlier. Okay, so we have the antiderivative of this is just the natural log of y minus 65. This is going to be kt plus c. All right, I want to solve for y. So therefore, I'm going to use e. I'm sorry. They use the word exponentiate. Exponentiate, sure. I never heard that before, but sounds good. Y minus 65 is equal to e to the kt plus c. There's no tricks here. There's no multiplying anything times the negative. It's just the way it is. All right, so now remember that this right here from stuff we talked about in the past, this is the same thing as this, and e to the c is a constant, right? And that constant, they call this letter a. So this is going to be a e to the kt. All right, so now I have a function that can determine the temperature of that drink. However, I am missing one aspect of this. What I'm missing is I don't know what k is equal to. Right, so I'm going to use, step number 2 is use the two temperatures that were given to you with the time attached to figure out what k is, right? So that's what I'm trying to do. So we know that the temperature at 10 was 35 after 10 minutes, and the temperature after 20 minutes, right, because 10 minutes pass after that, was 50. So this is the only part that's a little bit weird, right? This is not the only way to do it, but what we're going to do here is we're going to substitute that back. So I'm going to go back to this because it's a little faster, and I'm going to substitute that in, right? So we have y minus, excuse me, that's not correct. So I have 35 minus 65 is equal to a e 10k. All right, so t is going to be in minutes in this case. And then the next one is going to be 50 minus 65 is equal to a e to the 20k. And again, I'm trying to solve for k. So really what you could do if you wanted to, well, no, let's not do that. We can actually do a ratio here, right? Which is what I'm going to do. And it actually doesn't really matter which way you do the ratio. You can put one on top of the other, no particular order, and this will both work out. All right, so I'm going to do a ratio here where I just, let's see, what is this one? 50 minus 65, negative 15. I'm going to do a ratio over here. Okay. And that ratio should work because it comes from the same equation. It should have the same a and the same k here. All right, so if I do that ratio right there, that's going to give me a 2. So I'm coming here to the top. So that gives me a 2 is equal to e. Remember, e to the 10th k divided by e to the 20k, I subtract the powers. So I have e to the negative 10k. And again, I'm still in search of solving for k. So now I'm going to use the natural log of both sides. And when I do the natural log on this side, that's going to give me negative 10k. So k is equal to natural log of 2 over negative 10. See, that wasn't that bad. Just kidding. All right. So now, again, to figure out the initial temperature, I'm going to have to go back to this equation that I have here, and I'm going to plug that in. All right, so I have y is equal to, I just figured out that I may need to look for a. All right, so, okay. I need to know two things. Just realized that. So now I have e to the power of natural log of 2. And yeah, there's a way to simplify this more than what I'm doing, but I'm not going to go too crazy with this because it's complicated. It's already complex enough as it is, right? All right, so now I found the k. But now I have to find a, right? So I have to find that constant a. So to do that, what I can do is it doesn't really matter which function you use. In this case, I'm going to choose to use, what was it? 10 and 35, right? So y was 35. The temperature was, I'm writing too big here. The temperature was 35. So I guess I should call this step 4. So step 3, I found what k is. Step 4, I'm going to find out what a is. So I have 35 is equal to a e to the negative natural log of 2 over 10 times 10, right? T being that 10. Remember, after 10 minutes, the temperature was 35, right? So now all of this is some kind of constant now. So I have 35 is equal to, let's see, let me see if we understand one another here, right? So the natural log of 2, that negative, I can bring it to the top of this as a power. Okay. So plus 65. So this right here, the e natural log is going to become a times 2 to the negative 1, or I can write this as a to the 1/2 power plus 65. Now I can go ahead and solve. So this is negative 30 is equal to a to the 1/2. So I'm going to multiply both sides times 2. So a is going to be equal to negative 60. Okay. Whew. All right. So now I'm going to use, finally, I came up with my equation as it was. And honestly, the solution, the solution is only going to save you step number 1. So this is about all it saves you. After that, you really have to do everything else by hand. All right. So my temperature is going to be equal to, or at least this formula is negative 60 e to the power of negative natural log of 2 over 10 times t plus 65. Okay, so that's really the hard part. Now the easy part should be, what was the frozen coffee's original temperature? So we're going to plug in 0 for t. If I plug in 0 for t, right, and don't write this necessarily, but this whole thing goes to, no, well, not the whole thing. Yeah, actually, the whole thing goes to 1. All right, so then that would give me negative 60 times 1 times plus 65. So the original temperature was 5 degrees Fahrenheit. Wasn't that so simple? All right, let's go over the last one here. It says, when would the drink reach a temperature of 63? So you already did the hard part. All right, the hard part, you already have the equation that you came up with earlier, right, which I'm going to rewrite right here. So this right here, y stands for temperature, is equal to negative 60 e to the negative natural log of 2 over 10 plus 65 times t plus 65. Now it says when the temperature is going to reach 63. All right, so 63, set that equal to 63 here. And let's see. This is the natural log of 2 over 10 times t plus 65. And after that, really just a bunch of algebra. There's really not a whole lot of calculus involved after this. So subtract the 65. Now I will divide both sides by, oh my gosh, can't write. by negative 60, which will give me 1 over 30. Let's see, I have negative natural log of 2 over 10 times t. Okay. Let's see. So now I'm going to use the natural log on both sides. Ooh, yeah, that is pretty crazy looking. So when I use the natural log on both sides, it's going to be the natural log of 1 over 30 is equal to negative natural log of 2 over 10 times t. All right, and then now finally I'm going to divide both sides, or I'm going to multiply times the reciprocal of the natural log of 2 over 10, or the negative natural log of 2 over 10. So therefore, t is equal to the 10, or negative 10, over the natural log of 2 times the natural log of 1 over 30. So again, I'm going through a ton of algebra, all right? So I hope you're strong in it. And when I do that, I'll make sure, check this. Yeah, when I do that, I get 49.0689, okay? It says, what would the temperature of the drink be after 1 hour? So this is the easy part. Again, you already have the solution to the differential equation, which I will then rewrite here. And this one's easier because all I have to do is plug in, 1 hour. Ooh, almost got me. 1 hour is the same thing as 60 minutes, right? So just be careful with that. Everything I've been doing so far is in terms of minutes. So I have y is equal to negative 60 e minus, to the power of the natural log of 2 over 10 times 60 plus 65, and please put that on your calculator. So the temperature after an hour would be 64.063 degrees Fahrenheit. So look, wouldn't that make sense though? The longer and longer you wait, right, in your car, say that you're in the car for an hour with a drink, then the temperature of the frozen coffee is going to approach the temperature of the car, which in this case, the temperature of the car was 65. All right, guys, I know that was a lot. That was truly a lot. And let's just try to do all the homework and see what happens.